We're continuing with chapter 18 and actually going to finish it up, but we're going to look at examples using means instead of proportions for sample distributions. So our first example is about SAT scores, and SAT scores have been designed so that they have a mean of 500 and a standard deviation of 100. We want to know, what about the mean of random samples of 20 students? So again, we take a bunch of different samples of 20 students, calculate the average of each of those samples, and then plot them. That distribution will have a normal shape. Because we are using the random samples of 20 students, we can use the central limit theorem and then the 68, 95, 99.7 rule to see what the population will look like. So in this particular case, we're going to actually draw the normal model. So we start by drawing our bell-shaped curve, and we put our mean in the middle, which is 500. We need to find our standard deviation. Our standard deviation is going to be the standard deviation of the population divided by the sample size, by the square root of the sample size. So this will end up being 100 over the square root of 20, which ends up equaling 22.3. So 68% of the data fall within one standard deviation. That will be between a score of 477.7 and 522.3. 95% of the data fall within two standard deviations. So scores that are in between 455.4 and 544.6. And then 99.7% of the data fall within three standard deviations. So in between scores of 433.1 and 566.9. So this is how our distribution would look. Our second example says, suppose the mean adult weight is 175 pounds with a standard deviation of 25 pounds. An elevator in a building has a weight limit of 10 persons or 2,000 pounds. We want to know, what's the probability that the 10 people who get on the elevator overload its weight limit? Well, if the elevator can hold 10 people or 2,000 pounds, that means that on average, each person could weigh 2,000 divided by 10 or 200 pounds. What we're really looking for here is we're looking for what's the probability that the average weight on the elevator is above 200 pounds per person. I'm going to sketch the normal model because that's what we're going to use to solve this. And our mean is 175. And again, we're looking for the average person to weigh over 200 pounds on the elevator. So we're looking for that little shaded area right here. So we know our mean is 175. We need to know our standard deviation. Our standard deviation is going to be 25 over the square root. Our sample size is 10 people, so 10. And that ends up equaling 7.9. So then we calculate a z-score. So our z-score would be our observed value of 200 minus our mean, 175, divided by our standard deviation. And in this case, we end up with 3.16, which automatically, because the z-score is above 3, should send up a red flag saying that we are most likely not going to see this happen. But then if we do calculate the probability, so the probability that the average person weighs more than or equal to 200 pounds is equal to 0.000789. That's actually 0.0789% of the time, so it is not very likely. So the next time you get on a crowded elevator, you can feel pretty comfortable that it's going to be okay. Our third and last example today says, at birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds. a random sample of 34 babies born to mothers living near a large factory polluting the air and water shows a mean birth weight of only 7.2 pounds. We want to know, is that unusually low? I'm going to go ahead and draw a normal model to help calculate this. So our mean is 7.8, and then we're looking for the probability that 7.2 is underweight. So we want to know if that's unusually low. So we're looking to see what percentage is actually below that. When we calculate our z-score, it'll be equal to our observed value of 7.2 minus 7.8 divided by our standard deviation. So we have to calculate our standard deviation. So our standard deviation is going to be the standard deviation of 2.1 divided by the square root of 34, which is equal to 0.36. So we divide this by 0.36, and we get a z-score of negative 1.67. When we calculate the probability that the average weight is less than or equal to 7.2, we get a probability of 0.047, which is 4.7%. So 4.7% of babies are still born below 7.2 pounds, so it doesn't seem like it's too unusually low. It might be a little on the low side, but it might not be totally unusual. It just depends on what you consider to be unusually low. And this seems to be fairly normal. I want to talk a little bit about standard error. So in both sampling distributions, for both means and proportions, we know how to calculate the standard deviation. For proportion, it's the square root of PQ over N, and for a mean, it's the population standard deviation divided by the square root of N. And it makes it very easy if we know, or we can pretend to know, what our population proportion is, or what our population standard deviation is. Again, dealing with proportions or means. Often, though, we only know the observed proportion or the sample standard deviation, and we just end up estimating. This is called standard error. The thing about standard error is that it doesn't mean that there's actually an error at all. It just means that we're basing our standard deviation off of an estimate. So instead of actually calling it standard deviation, we call it standard error if it's based off of an estimate. If it is based off of the actual population proportion or the actual population standard deviation, then it is the true standard deviation. However, if we are just estimating or kind of pretending we know what the population proportion is and what the population standard deviation is, then it has to be called standard error. So again, it's just that standard error is a much shorter name than the estimated standard deviation of the sampling distribution of the sample statistic. That's a lot to say. Standard error, much simpler. There are two basic truths about sampling distributions. Sampling distributions arise because samples vary. Each random sample will contain different cases and thus different values. Even though we can simulate a sampling distribution, the central limit theorem actually saves us the trouble if we're dealing with means and proportions. So we could actually go out and simulate or take 1,000 different samples and then plot all of their statistics. Or we can just use the central limit theorem and say, hey look, we're pretending to do this, and then it works out the same. But what can go wrong? So we don't want to confuse the sampling distribution with the distribution of the sample. It's very easy to do so. When you take a sample and you look at the distribution of the values, usually with a histogram, you'll calculate a summary statistic. For categorical data, this will be a proportion, and for quantitative data, this will be a mean. The sampling distribution is an imaginary collection of values. So again, we're just pretending to go out and calculate all of these samples. Of course, they did do that at one point to figure out that this works, but we don't have to anymore. So we're just kind of pretending to. And we're taking all of the values that a statistic might have been from all of those random samples, the one that you got, and the ones that you didn't get. That becomes your sampling distribution. We also need to be aware of observations that are not independent. The central limit theorem depends crucially on the assumption of independence. You can't check this with your data. You have to think about how the data were gathered. So you have to make sure that the observations are independent. And then you want to watch out for small samples from skewed populations. The more skewed the distribution, the larger the sample size is going to have to be for the central limit theorem to work. So I want to kind of wrap this chapter up and think about what we have actually learned within this chapter. So sample proportions and means will vary from sample to sample. That's sampling error, or another word is sampling variability, and we expect that. Sampling variability is unavoidable, but it is also predictable, which is another reason why we are able to use the sampling distribution models and use the normal model. We've also learned how to describe the behavior of sample proportions when our sample is random and large enough to expect at least 10 successes and 10 failures. And we've learned to describe the behavior for sample means, thanks to the central limit theorem, when our sample is random and larger if our data comes from a population that is not already unimodal and symmetric. So again, we can use the normal model for sample proportions as long as we have at least 10 successes and 10 failures, and we can use the normal model for sample means as long as our sample is random and it has a large sample size. Alright, but that is it for chapter 18. I will see you guys tomorrow. Have a great night.